Hello everyone, my name is Howie and this presentation is about better Scala builds with the mill build tool. So the motivation for this presentation is that although the Java language is known to be very performant, very easy to learn and have great IDE support, Java build tools like Maven or Gradle don't always live up to that expectation. So this talk will discuss what are the problems with these existing build tools or the limitations, why build tools are fundamentally a pretty difficult problem to make easy to use, and we'll explore some alternate designs and implementations that try to improve upon the status quo that we have today. I guess first about myself, I learned Java in 2004. Back then you didn't have generics, you had to cast everything you took out of a linked list or array list before I could use it. And it's been a long journey of 20 years since then. I've been doing open source projects since 2012. My last job was at Databricks, as you see, so a lot of the projects were in Scala on the JVM, since that's what Databricks use, but also a lot of other Java and JVM related projects. My professional work is specialized around developer tools, so build systems, CI systems, testing systems, everything that goes on before your project goes to production. This talk will have 4 sections. We'll talk about can Java build tools be better? Is it even possible to improve, or is it already the best we can expect? We'll talk a bit about Mill, which is one of the open source projects I've been working on that tries to explore this problem space a bit. And we'll talk about what concrete improvements that we can demonstrate. And one of the interesting ideas, which is these object-oriented builds down at the bottom, that the Mill build tool does very differently from most other build tools out there. First, can Java build tools be better? Everyone uses Java build tools, right? People don't use Java C or Java from the command line just raw, because you need the things that build tools do. Build tools provide dependency management, scheduling, parallelism, all sorts of other interesting things that you actually need on their day-to-day work. But I think most people agree that build tools like Maven or Gradle, sometimes there's room to improve. You can get frustrated with them. For me personally, my problems with these tools largely fall around these categories: performance, IDE support, and programmability. And we'll talk about each one in turn. So first, performance. Most people don't realize how fast the Java language compiles, because you use Java through Maven or Gradle. It doesn't feel as snappy as, for example, using Go or using some other programming languages where you just press compile, it's instantly complete. But it actually is very fast. So you look at, for example, the Netty code base. You all be familiar with Netty. It's Java's most popular async networking server. It's 500K lines of code, not a small project. On my laptop, it takes about 50 seconds to compile in parallel. So I can kick this off now just so you can see. Copy paste this over to my Netty code base, and we're not going to wait for it. You'll just see the timing later when it's done. And so 50 seconds, right? Is that good or is that bad? That's hard to answer in isolation. If you look at any individual module within Netty, for example, Netty Common, it takes 29,000 lines of code, about 4.5 seconds. So it compiles about as quickly. And this is just pure compilation in this case. No C code, no dependency resolution, just a compile. So if you take this out of Maven, you just run Java C directly from the command line, you'll see that it actually compiles 3 times faster. So you run Java C with this very long class path I shrunk, just like a fit on the slide. This is basically the exact same command that Maven's running internally. You see that Maven actually adds 3x overhead over just shelling out to Java C. And running Java C like this is actually the slowest you could ever make Java C perform. And who knows why that's the case. Why is Java C from the command line always the slowest you can make Java C run? Yes, it's because it's cold. Java C is a Java application, and Java applications run on JVM. When run cold, they take very long to warm up, and they don't have time to get JIT optimized. So this is actually the worst case. You'll never run a web application or backend application like this that's running it cold every time. But that's already 3 times faster than Maven. So if you run Java C hot, and to do this, I set up this bench.java file. I can show you here. And all this does is this has a while loop, and this while loop just runs a Java compiler in memory. Most of you won't use the Java compiler API directly, but it's there. And if you do this, you'll see that it runs in 0.3 seconds, down from 4.5 seconds from Maven. So in theory, Java should compile at 100,000 lines of code a second on one core. We should be able to compile the whole of Netty in 5 seconds on one core. It should be basically instant for most of the things that you do day to day. So it's not the case, right? We see it's taking 50 seconds to compile Java C on 10 cores rather than 5 seconds on one core. And I'm just going to show you the other examples live. So sorry, let me make this a lot smaller. If you run Maven clean compile here, it'll take about 5 seconds. So I'm not timing the clean, just cleaning, so it's a good example. So this is compiling just netty common, takes about 4.3 seconds on the command line. If you run javac from the command line, it's faster than that. I think when you run time javac, you'll see it runs about 1.5 seconds. And if you run this bench.java file that keeps javac warm, because that's how JVMs are meant to be run, right? They're meant to be run warm. You'll see that it runs over and over, gets faster and faster as we just sit here and watch, just because that's what the Java hotspot optimizer does. And after a bunch of time, let me try and find a good, here we are. You'll see that now we are compiling the same 29,000 lines of code, but instead of taking 4.5 seconds, we're taking 260 milliseconds, compiling 110K lines a second. So back to the slides. So compilation isn't everything. Like you obviously do many other things in your day-to-day work, and Java compiles are still kind of acceptable, but it just kind of shows the amount of overhead that build tools can provide, can give you on top of the underlying tooling. Like Java tooling actually is very fast. Creating jars, creating assemblies, and all that can be made very quickly, but your build tools often don't expose that raw performance. And you can see that here, where compiling something with Maven is 15 times slower than it should be compiled with javac kept warm. The next thing we're going to look at is IDE support. So all of you use IDEs probably, and IDEs are great. But when you use something like Maven or Gradle, the IDE support is often not as good as you'd expect. So here's a Mockito project. Mockito is the open source unit test mocking library. You'll see that it does have some IDE support. You can jump around a bit. You can ask for types and documentation. But if you jump to things, you often hit these getters and setters, where in this case, I haven't set up the source code, but even if you set up the source code, you'll see that it's just a getter and setter with no indication of where the values are coming from. Like I'm adding something to JVM args, but who's using it and what was the value before I added, I have no idea. So if the documentation is good and you memorize documentation in your head, you know what these things do. You can Google things, ask ChatGPT. But fundamentally, the IDE just doesn't help as much as you'd like. That's why you need to go and reach for these third-party documentation, AI apps or whatever, or Google. And this is not the experience you expect, like working with a JVM project, right? Like if I open up any code in the Mockito repo, I'm just gonna pick a random thing, maybe, I don't know, argument captor test. Not all these things have documentation, but despite that, I can jump around to anything I care about. Like I don't know what's argument captor, I can jump to it. I don't know what's capturing matcher, I can jump to it. I don't know what's reentry read write block, it's in standard library, I can jump to it and see it there. So that's the kind of difference between the IDE support you expect from a Java application, which is very good, and IDX support you get from build tools like Gradle or Maven, which is a bit superficial. Like you can get a bit of stuff, but it stops you from really understanding what the build tool is doing. And when you think about it, fundamentally the reason why this is the case is that Maven and Gradle and other build tools are generally built around these global variables, like get compiler args can be getted or setted, JVM args can be getted or setted, but just because you wrap the global mutable variable in the getter or setter doesn't make it any less global or any less mutable. And both humans and IDEs are IntelliJ can't really understand what the global mutable variable is doing. That's why we have a problem here. And the thing is, if you wrote your production code with global mutable variables, you'd have the same problem. But people don't write production applications with all these global mutable variables. That's why they don't. But somehow the build tools have this problem, use global mutable variables, and that's why the build tool IDE support, despite being the same language or JVM languages, are not as good as what you'd expect from a JVM application. And here I show you the Groovy DSL, but the Kotlin DSL has the same problem. The problem in this case is not the types, but the mutable variables or global mutable variables, particularly, that make it hard for IDEs to help. The last thing we're going to discuss in terms of problems with existing build tools is programmability. So ideally, if your build is always standard, there's nothing for you to configure, it's great. But if you do have to configure stuff, maybe you have a custom bill of materials, maybe you have a custom deployment artifact that some infrastructure team in your company wants you to provide, maybe some custom linter that you're trying to experiment with, you often need to customize your build tool, and there may not be plugins for you to do it if it's something bespoke. So as a representative case, I'm just going to look at this requirement to save the project line count as a txt resource file to use at runtime. So this is trivial, like any new grad should be able to bang out this kind of naively in 30 seconds without errors. But if you want to do it in a kind of build tool, it gets a lot more tricky. It's not impossible, like here's an example with Maven using the exact Maven plugin. But it's a lot of things that you have to consider that you may not have thought of immediately. And the first time you do it, you'll probably get it wrong. Like it doesn't work on Windows because it uses bash. Your ampersand need to be escaped. If you don't use ampersand, you'll find your errors get silently swallowed because it's bash. Generate sources maybe don't work. And there are other ways to do it. They're all doable. And I'm sure all of you have done all these other different ways. I have done all these different ways. But it's a lot more tricky than what you'd expect, which is a 30-second exercise with no errors. Gradle has a different set of trade-offs. So Gradle is, in this case, using Kotlin. So the Kotlin DSL runs multi-platform, no Windows problems. But there's issues around like kind of wiring up your custom logic, in this case, the walking file system tree and counting the lines, to all the Gradle build graph. So Gradle has a graph data structure used to parallelize and orchestrate your build. And it's very easy to get that stuff wrong. So there's actually a bug in this. And let's give you like 30 seconds, see if anyone can spot it. So here's the most naive custom task using Gradle. It's using one of Gradle's 5 different DSLs. So Gradle has Groovy, 3 Kotlin DSLs, and a declarative DSL they're working on. So it is just a representative example, right? It's not the best Gradle code, but it's not the worst Gradle code either. So where's the bug in it? It's like the most trivial hello world task you could ever think of. So the bug in this is we are watching source main, and we're actually only using source main Java. So every time you make a change to source main resources, source main template, source main anything else, you'll be unnecessarily recomputing this code, and it'll make a build slower. And it won't make a build incorrect, but it'll just be non-deterministically slower depending on what you're touching. And so that's the kind of problem that makes configuring existing build tools like Gradle or Maven kind of tricky, right? Like it doesn't get wrong, but it's very hard to detect these errors, and your build will either get slow if you watch too many things, or it gets flaky if you watch too few things. And you can't catch in code review, or a whole room of you couldn't find this bug on the most simple Gradle custom task. So that's why these things slip into your code base master branch, and that's why your builds end up being slow and flaky, because of this challenge in programming, customizing a build tool. And even if you're not the one customizing it, the plugin authors will have the same problem. So the plugins you use will also have bugs that they did not catch in code review, and your plugins will also be slow and flaky, unnecessarily slow as a result. So that's kind of the problem statement, right? Like your build tools are important. Everyone uses JVM build tools. The whole ecosystem is built on them, but there are some areas in which they can be improved. Or at least I think they can be improved. And maybe it's worth looking at like, why are build tools so complicated? Like, why can't people just make build tools as simple as making any other application like Hello World, FizzBuzz, or To-Do MVC? And I think the reason for that is your build tools actually do a lot of things that you don't realize until you actually need to kind of configure them correctly or debug problems in them. So not only do you need to care about your application code, but you also need to care about what your build tool needs to do. Maybe it's counting lines and adding it to a resource file. And then after that, you also need to care about what task depends on what, who runs in what order, what can be parallelized, what's a CLI syntax, or have a separate syntax, or you use some existing syntax. All these things that your build tool needs to manage. And you can imagine if any of you just naively go and make an API that models all of these things, it will be quite a complicated API. And so that's why build tools are fundamentally a pretty challenging task or problem space to work in. So that's the first section of this talk. Like, why can Java build tools be better? In my opinion, yes, but it's not so easy just because build tools are actually quite complicated pieces of software. Next, we look at the Mill build tool, which is one of the open source projects I've been working for a few years. So Mill is a kind of exploration in whether Java build tools or JVM build tools in general can be different from how they are today. So it targets all the different JVM languages, Java, Kotlin, Scala, and it tries to improve upon the things that the existing Java build tools fall short. It's not a huge project. There's like a few guys committing, maintaining, some contributors. There's a small community around it. But it's definitely not as battle-tested for 20 years as Maven or Gradle is. So that's just to set expectations. So a simple Mill build looks like this. You say object foo extends Java module. You define some dependencies. You object test suite inside foo with its own like Java test superclass and JUnit 4 like interface. And you can use foo.compile, foo.run, foo.test, foo.assembly, run the assembly later on the command line, just normal build tool stuff. So the syntax is a bit foreign. So Gradle uses Groovy or Kotlin, Mill uses Scala, but hopefully it's not too complicated and you can more or less guess what these things do. You know what packages and imports and methods and objects and classes and extends do. So you can probably guess what all these things do, even if you've never written Scala before in your life. A more complete example may be something like this, which is a Spring Boot to MVC example. So this I'm going to show you live. Where is it? Spring Boot, Spring Boot. Okay, I don't have it open. Let me just open it. Spring Boot to do MVC. So this is it in IntelliJ. You can see it has a lot more than the hello world. It has web jars, it has unit tests with H2, it has integration tests with test containers and Postgres. If I go to this folder, I can do mil compile, I can do mil like foo.test. I think it says test in this folder. I can also run tests from the command from IntelliJ. So if I go to my test suite here, I think I can just run this test like that. You see it runs Spring Boot and runs a test. You can do it, you can run it interactively. So I can do run background. Maybe I'm going to --watch. Now if I go localhost 8087, this is my Spring Boot app that's running in my terminal. If I go to my resources and change, for example, to-dos to hello, like Geecon, you'll see that now Spring Boot takes a moment to start up. Now it says hello Geecon. The CSS doesn't quite work, never mind. I can rerun the tests. You'll see now the tests fail because the tests were asserting that you see to-dos on the home page, and now we are not seeing to-dos on the home page anymore because it's hello Geecon. So that's the Spring Boot example, just to show you what this kind of works around mil and Spring Boot. So people often ask, like, what does mil support? And the answer is it supports most of the open source frameworks and tools. Not all of them, but most of them. Things like JUnit, Kotlin, Micronaut, Maven Central Publishing, Sonatype Central, or OSSRH can just all do all of these things. Annotation processors like Lombok. And it won't support the internal stuff you have. So if you have internal plugins or internal customization to Maven or Gradle, mil won't know about those. But at least all the open source stuff is there, and you can customize it yourself quite easily, which you'll see later. So that's a mil build tool, right? And we saw what it does, which is the same as all the other build tools. You can compile, run, test, assembly, IDs, all that, --watch. So far, not so interesting. So I think the next section is where it gets more interesting, where we talk about where mil is different from the other build tools. And again, it comes down to the three areas of performance, ID support, and programmability. So first, let's look at performance. We use Netty as our case study. So Netty, as you already saw earlier, quite a big project, quite a big build config, 50 sub-projects. We ported it from Maven to mil manually. It took about a day or two. And we ported enough that all the tests passed on the mil build. So we got all the flags correct, all the JVM flags, compiler flags, and so on. And we found that it's a lot faster to run in mil than in Maven. So there's a number of reasons. It's actually using the same Java compiler. It's the same Java version, but we have like the mil build is more effective at parallelizing it, and it keeps the background daemon, so you get more of the Java's kind of hot performance rather than the cool performance that Maven gets. And I can show it to you now. If I go back to Netty, if I do /mil compile, /mil clean and compile. So to be clear, this is cleaning, which is deleting all the class files. I need to compile everything again, but I'm keeping the daemon running, so mil is able to kind of keep the JVM in Java compiler hot in memory. So first time I run it, it may take a bit more than 10 seconds because it's Java JVM program, it's cold. It took 15 seconds. Next time I run it, should take about 10 seconds. And I've actually counted the logs and looked at all the number of files it says it compiles. And it's the same number of files and the same modules. It's just much faster than it was using Maven. And to be clear, this is still not as fast as it should be. Like, we should be seeing 5 seconds on one core to compile 500K lines. We are actually seeing 10 seconds on 10 cores. But it just shows you how much room there is to improve. And things like incremental compiles are also a lot faster. So if I do, for example, if I don't clean things and I compile again, mil's much more quickly able to see that there's nothing to do. In about half a second, it says, okay, nothing to do, exit, because everything's already compiled. Whereas if I do the same with Maven, without the clean, you'll see Maven actually takes quite a long time to figure out and scan and load and class load and realize that it's able to exit. So that's compared to Maven. Gradle, the difference is not as stark. We use Mockito, which is built using Gradle as our example here. 20 sub-projects, again, ported to mil manually. And here, instead of seeing a 5x speedup, we see about a 3x speedup. So Gradle already does have a long-lived daemon, which keeps the compiler hot in memory. But nevertheless, there is a lot more overhead in Gradle than mil, and you see this in the numbers, how long it takes to do the exact same things. Well, compilation performance is not everything. There are a lot of other useful things that we put in, like this --watch we saw earlier. There's selective execution. So if you make a change to one module, Mill can do the breadth first search and see, okay, you change this, affects this, therefore affects this other test. And so you only need to run that test, but don't need to run all the tests that are unrelated to your change. This is very useful in big mono repos and stuff where most changes don't touch the whole repo and touch like some subfolder. Mill can just help you run those tests automatically and downstream tests. Assembly jars can be made a lot faster. So assembly jars are just zips, and zips can be updated incrementally very efficiently. I don't know why Maven and Gradle don't do this, but you make like a 200 megabyte Spark submit assembly, for example. The first time you create it is going to take about 20 seconds. That can't be avoided. But you add a new file, recompile, and update the assembly can take less than 1 second, just because you can just take out the old file, put the new file in, kind of without having to recreate the whole thing from scratch. And this is something that Mill does for you. The Chrome profiles are quite nice. So every computer, all of your computers have this built-in Chrome profile visualizing UI. You probably don't know it. Who's used this before? Nobody's used this before. One person's used it before. But if I take, for example, my Netty build I saw earlier, I compiled everything in about 10 seconds. It generates this Mill Chrome profile.json file. So this is a standard format defined by Google. You just drag this into Chrome, and you can see where my time is going. Okay, here's not so interesting because this was a no-op compile, but let's do a clean compile. And I guess even before it's finished, I think I can drag it in. And like already, you can see where the time in your build is going. So you can see where your cores are well utilized at the back of at the front. You can see where it's bottlenecked on common compile. And when the build is finished, which is about now, I can drag it again to see the updated version. Yeah, and it just gives you a good sense of where the time is going, which I think is a question many of you ask, like when you're working in your developer tools, like you ask, why is it slow? And Milk is able to answer that quite easily. You don't need to go sign up for Gradle Enterprise and set up a self-hosted Gradle Enterprise server, upload build scans and all that. You just take the JSON file, load into Chrome, and you can see that, okay, microbench is taking a while. Maybe that can be improved, broken up. Common compile is taking a while. Maybe that can be improved somehow or broken up. And you can already have like some ideas of what you can do to improve your build, even if you don't know anything about Mill and you don't know anything about, in this case, the Netty code base. So that's the performance angle, right? The compiles are a lot faster, which is nice. But as you know, Java compiles are already not the worst, but they're faster, and there are a lot of other features that help make things a bit better. They are not rocket science, but we do it, Mill does it, and other build tools don't, or don't do it quite so easily. Next is ID support. So earlier we looked at the Mockito Gradle build, and I'm going to also open up the Mockito Mill build. So over here, I have the Mockito Gradle build on the left, Mockito Mill build on the right. This is for the error-prone submodule on both sides. First thing you'll notice is that it looks very similar, and that's because like we are configuring the same setting, passing the same flags to the same Java code to the same Java compiler. So we have to have a lot of the same information, dependencies, fork arg, compiler args, third-party dependencies, and so on. But where things are different is that where Gradle is configured by mutating these global mutable variables like plus equals JVM args, Mill is configured by overriding, you see this little override IntelliJ symbol here, these methods. So the naming is fork args rather than JVM args, but what's important is I'm overriding a method here. And the syntax is Scala, so it might be a bit foreign, but hopefully you can guess what's happening. And it's familiar enough that IntelliJ can tell you what you're overriding. So I can see that, okay, IntelliJ says that you're overriding fork args from run module, great. Fork args, I can just search where it's used. Fork args is using runner. Maybe I don't know what runner is, but I can search where it's used. Runner is using run background. Runner is using run forked. Run forked is using run. And just like that, you can kind of see and debug your Mill build to see not just what the type of this variable is or what the documentation is, but how does it actually get passed through my build pipelines to affect the final result I care about. So you can trace for downstream, which I just showed. You can also trace upstream. So for example, I don't know what final main class is, or let's say I do know, but I'm not sure how it's computed. I can jump to it. No Java doc, but not a problem. I can see its implementation here. I can see its final main class opt. I can jump to that. Again, no Java doc, but I can look at the implementation and say that if main class is defined, I use that. If main class is none, which is not defined, I use all local main classes. Again, I don't know what this is. I can jump to that. You can see, okay, now I'm using class graph, which is an open source project, to scan the class path and look for the main method. So in contrast, you try to do the same in Gradle, you kind of go nowhere. And again, you can Google things for Gradle, you can ask Stack Overflow, you can ask ChatGPT. You can do all the same things in Mill, so that's not any different. But where Mill is different is that Mill lets you explore your project or your build with your IDE the same way you explore any application code base. Like you already are jumping around your application code using IntelliJ day to day, and Mill lets you do the same with your build code. And so this doesn't matter when your build is perfect and nothing is broken. But when you're trying to fix something, something's misbehaving, some new plugin doesn't work with some other plugin, some flag isn't working the same way it says on the documentation, or documentation's out of date and doesn't have some new feature. Being able to dive through your build in your IDE is a really nice kind of escape hatch. So you never get blocked just because you can't figure out what to Google and to get the right results. So that's IDE support angle, which I think is quite interesting. The last thing to look at is programmability. So I guess maybe the first thing to mention here is that, as we saw earlier, there's a lot of things supported out of the box, maybe more so than other build tools. So you don't need to reach for plugins so quickly or customize things so quickly. Like you need JNI support, you need Kotlin support or something, it's built in. But when you do need to extend your build or write your own plugin, which often happens, what's interesting is that where most build tools need some kind of plugins, Mill just lets you write code to do what you want. So this removes this middleman where I want to use X, but I can't use X unless I use the X plugin, and X plugin is unmaintained by some guy 5 years ago on GitHub, and then you have some question, do I need to maintain X plugin? Do I fork it? Do I make my own X plugin? So Mill just lets you use X directly, and you'll see what that means. So back to the code. Here it is. Okay, I'm just go here and clean my terminal. So this is like the minimal Mill build you see on the right. There's nothing here. Mill follows Maven with this kind of convention over configuration. So if you're just using the default source folders, default resource folders, there's no, you just extend the Java module superclass and you get all that for free. There's nothing for you to configure. But let's say I wanted to count the lines of code in this project and add it to a resource file. How do I do that? Well, in Mill, you do this by saying line count, defining a method. Using Scala syntax is def, so hopefully you can guess what that means. I wrap in a task and I say, well, I want to look at the sources. If you're not sure which sources you want to look at, you can ask IntelliJ. You can say, okay, I have all source files. I map them to the file path. I want to read all the lines of that file path, get the size of those lines, and sum them up. And this is all you need to do to define a custom task in Mill. You're basically defining a method that calls other methods, in this case all source files. You're not sure what the other methods do, you can jump to them. There'll be documentation, implementation, all that. And I can now do Mill show foo.line count. Okay, it takes a moment to compile. I can load the JVM. Okay, 17 lines of code in this project. I can do inspect foo.line count. You can see that we get the Java doc captured for you, line number, file name. We even capture the methods you call. So you called foo all source files on the right, we captured on the left. You can debug your code in the command line. So that's all you need to do to define a custom task. You notice there's a lot less, I guess, boilerplate than most of the other build tools. Next, let's look at integrating into resources, which we haven't done yet. In Mill, if you want to override the resources to include something new, this is done by using JVM overrides. So you def override def resources. Again, if you're not sure which resources you want, your IDE is happy to help. Equals task. This is the Scala syntax for type annotation. So in Scala, type's on the right rather than the left, like Java. But hopefully you can see what this means. I can do call super, and I'm going to write my resource file to this task.destination folder. And it's going to call line count as a string. And I'm going to append a reference to the destination folder to add it to my resource path. So I'm not replacing the resource path, but I'm taking the super resources, which is a normal resource folder, and appending a one element sequence with a path reference to this task.dest. So what's task.dest? Well, in Mill, every task gets its own destination folder, and these destination folders are unique. So what's the problem with file system? Like the file system is a big global mutable variable effectively. Anyone could write anywhere, you'll stomp over each other, you don't know who wrote to where and where the values are coming from. And it's the same problem we had earlier in the Gradle code, except on the file system, it's even worse because you can't even jump around your file system using IDE. You kind of have to guess who's writing to these files. So in Mill, we give each task its own folder on disk, and you can see it here where you do Mill show foo.resources. So now we have let me make this a bit longer. So we have the foo/resources folder, that is a super resources we saw earlier. But we also have this out foo/resource.des folder, which is a task.destination folder. And the point of this is only one task can write to each destination folder. Your global mutable file system becomes a local mutable file system. It becomes much easier to reason about, and we'll see why in a moment. And now that we have this override with def resources, I can do milfoo.run, and I'm able to have my kind of application code, just a simple hello world here, read my resource at runtime and print it out the line count. So just coming back to the slides, the line count is kind of a trivial example, right? It's not, no one actually does this, but this is just an example to show how you can extend mil using concepts like methods, like overrides, like supers, rather than having to learn a special like build tool specific concepts like phases or registration pattern or depends on and so on. So you just kind of define your own methods, calling other methods, override some of the methods you need to override. And these behave exactly the same as you learned in Java 101, despite the syntax being a bit different. So let's extend this a bit. Let's say instead of having a file system, a line count.txt file, I want a line count HTML file. So mil doesn't come built in with any HTML templating library, so this doesn't work. What mil does is it gives you the ability to import these libraries directly from Maven Central on the fly. So I can say import timeleaf 3.1.1.release, let's say. And now if I reload my IDE, we should see that this starts working, and I can now see timeleaf in my IDE libraries panel. So I can now say I want to import the timeleaf context, import the timeleaf template engine, and I can define a new method def HTML snippet, which is a task. And I want to say val context equals new context, context.set variable line count to line count as a string. And I want to say new template engine dot process. I'm going to copy the template from the slides because it's a bit finicky to type out. Dot process with this context. I think update this to line count. And now I can use this HTML snippet in my resources. And now if I do foo.run, I can see I'm pre-rendering HTML file on disk as part of my build. So I can look at out foo HTML snippet.json. You can see my cached HTML here with pre-rendered HTML here with some metadata, so mil knows how to invalidate it. And that's all I need to do to use timeleaf in my build to pre-render some HTML. So I think what's most interesting here is that there is no mil line count plugin, there's no mil exec plugin, there's no mil HTML timeleaf plugin, because with mil you can just write the code to do the stuff you want. And if the stuff you want requires third-party libraries, you use the third-party libraries directly. Like you're already using timeleaf in production, like you just use that rather than having to find some third-party mil timeleaf integration for you to integrate into your build. And this applies to anything, right? Like if you have some other libraries you want to use in your build to pre-render, pre-build some stuff at build or deploy time, you can do so just by importing it in your IDE using this syntax. And it works on command line too, as we've seen. So back to slides. Okay, this is example we saw. So just to compare this extension model of mil versus the existing build tools, the first thing you realize is that they actually are very similar. They contain the same information, and the Maven example does have imperative logic in it. So just because I take my bash script and wrap in a bunch of XML doesn't make it a declarative bash script. It's just imperative bash script wrapped in XML. So the other thing you realize is that the imperative logic often isn't the most difficult part of the build tool. Like you can get this off Stack Overflow in about 30 seconds probably, or ChatGPT can spit it out. But it's all the other stuff, like making sure you have the right goal, right phase, right version of the exact Maven plugin. That's the stuff that's maybe a bit more tricky. And it's not rocket science, but it's non-trivial. And compared to Gradle, right? Like Gradle uses imperative logic similar to mil. But again, the difference is that with Gradle, there's so much stuff you can get wrong that's unrelated to the build logic you want to implement. Like you can get wrong all these different depends-ons, input files, output files. And this code to actually walk the file system is not that hard. You can get that right without a problem. But it's the other stuff that is tricky. So with mil, we've managed to kind of automate all the other stuff, so you don't need to register dependencies. You call all line. When we call all source files, you get a dependency automatically. You don't need to write something to disk. When you return line count, it gets written to disk and cache for you automatically. And so when all that stuff is automated, your build logic suddenly doesn't become so scary anymore. It becomes quite small and easy to read, in my opinion, versus this kind of monstrosity on the right where it's so many things you can get wrong. And again, this is not the best Gradle build. There's probably better ways to do this, but it's kind of representative of something you might find in the wild. So that's the programmability angle. I guess the last thing we're going to look at is this idea of object-oriented build. So we saw that kind of briefly and just touched on it. But I think this is something that Mill does very differently from the other build tools that makes it very interesting. So every build tool has the same requirement, which is you need some kind of templated, customizable graph computation. And this is a bit of a lot of words, but for example, if I have a foo.bar module that's used by a foo module that's used by a quux module, foo.bar sources need to get compiled. Its class path gets used by foo.compile, gets used by foo.classpath, gets used by foo.assembly, gets used by quux class path, quux.assembly. So you have this build graph. Every build tool has a build graph. Maven, Gradle, Bazel, they all have build graphs. And you need some way to specify this build graph, right? And this build graph it needs to be templated because all your modules look very similar. It needs to be customizable because they're similar but not quite the same. For example, foo.bar class path doesn't depend on anyone upstream, whereas foo.classpath and quux.classpath does. It's a graph because you need to be able to schedule and parallelize your build. And it's a computation because you actually need to do the thing at each step. So you need to either have a bash script, a Java program module, or Groovy Kotlin module to actually do that. So some tool can hide this behind plugins, but this still affects you because if the plugin author has trouble doing it and the plugin author gets things wrong, then you get the buggy plugin. Or if the plugin API is complicated, you get two plugins that don't work well together. So this still affects you even if it's hidden behind plugins. And Mill needs to do all the same things too, but the difference here is that Mill is able to reuse concepts that you already know in order to implement this. So when we look at object foo extends Java module, this is literally a Java class that's extended by an object. So when you have a Java class, you get all of its methods. They call each other. So foo.sources gets called by compile, gets called by classpath, gets called by assembly, along with resources. And you already know how this works. So if I add line count as a new method that calls all source files, I override resources, and I call super.resources, but also call line count. You already know how this affects the build graph or the call graph. I don't need to teach you because these concepts are not new to Mill. These concepts are the same you learned in Java 101. And once we have this graph, we can say, for example, the blue steps like foo.compile and the red steps can run in parallel because they are not related on the graph. The green box foo.assembly needs both of them to finish before it can start. Once we have these objects with methods, we can give each method and object a name, like foo.linecount, foo.compile, and we can assign them paths on disk automatically based on that name. So you don't need to say, I'm going to write this to this file and hope no one else stomps over it. Mill does that for you and can guarantee no one else will stomp over it. And the JSON files for the metadata that you return, and any files go in this task destination folder, because as you know, build tools often work with files. And the nice thing about Mill doing this is that we can assign each task a different cache on disk, both for metadata and files, so they'll never collide. You never need to worry about these kinds of things with Mill. And lastly, Mill can do invalidation for you. So if you touch the resource folder, which is now super.resources because we overrode it, Mill can just do a breadth first search, see foo.resources is downstream, foo.assembly is downstream. Mill knows it needs to reevaluate these in order. You can use the topological order using Tarajan's algorithm or something. And Mill can also know that if I need to reevaluate foo.assembly, Mill knows where to delete the stuff before because it's all in the standard foo/assembly/json.des folder. And simultaneously, if I want to reuse the values from foo.compile and foo.linecount, Mill also knows where those things live because it's in the foo.out foo.compile.json out foo.compile dest, and similarly for line count. So what's most interesting here is that when you look at the build config on the left, we are implementing a custom task, kind of small little build pipeline with a custom line count task, an override of resources that integrates this into my resource path for use at runtime. But there's no depends on, there's no creation of the graph manually, that I'm not registering any callbacks. There's no parallelism in this code. There's no threads or executors or locks. There's no cache logic. There's no cache key computation, cache invalidation, cache reads, cache writes. And we have all that. It's just all taken care of for you behind the scenes. So you kind of write your pure build logic, so to speak, without all these build tool concerns, and Mill as a build tool does it for you without you having to do it yourself and possibly get it wrong. So if you come back to the slide of like why are build tools complicated, Mill also needs to do all these things. Mill also needs to take care of what depends on what, who can write to disk where, how are things called using the CLI. But the difference is that rather than coming up with like a bespoke API with a bespoke concept for all these, like a task depends on graph and build phases and all that sort of thing, Mill is able to really leverage the stuff you already know. So what task depends on what needs to run in what order, what parallelizes and what can't, well, that's a method called graph. You have a graph when the methods call each other, and from the graph we can derive all these things, and you already know how method call graphs work, even if you never studied like programming language theory. You've been using them for 10, 20 years. And on the other side is kind of the object-oriented side of things, where how are tasks run from the CLI? Well, in object-oriented land, you say foo.compile, so in Mill, we say foo.compile from the CLI. And similarly, where they redirect to disk is out/foo/compile.dest from the CLI. I have an extra foo here, it should be out/foo/compile.dest. And again, all these things that can be answered for you because Mill really like embraces the object-oriented nature of the build data model. And you don't need to learn something special, right? Like, look at overrides. Overrides are actually quite subtle, right? Like you have overrides, the guy who calls the previous method now calls override. There's a super, like which super do you actually call? But in Mill, because we use overrides from the JVM, you already know the answer to all these questions. And they're not simple answers, but you learned them kind of many years ago, and you can just reuse them here now. So I guess the long and short of this object-oriented build idea is that when your builds are just calling methods and objects inherited from classes, it works a lot better than the global variables you work with in Gradle or Maven or on other build tools. Like IDEs are very good at understanding methods calling methods. So IDEs can explore Mill builds very well. IDEs are very good at understanding inheritance hierarchies, so IDEs can follow that. So all the IDE support I showed you earlier, there's no custom Mill logic. It's just a standard IntelliJ with the standard plugins that's able to understand Mill builds because they're standard JVM programs. All your extends, override super, all work exactly as you expect. And you just write your object-oriented code and Mill handles all the rest for you. So things like, you always get the good performance because you won't have some guy forgetting to cache things or oops, I depend on too big a folder now, I'm rerunning things unnecessarily. And you don't need to clean as often because you don't have the flip side where someone forgot to declare a dependency and now your build is inconsistent and fails non-deterministically depending on what you run in what order. So Mill does that for you and you get the good, kind of the best of both worlds without having to do anything yourself. And this makes life easier for everyone. So like it makes life easier for you as a build author, for the plugin maintainers who also don't need to deal with all this complexity, and also for Mill maintainers like myself who are able to spend time doing interesting things like incremental assembly jars rather than trying to fight with the details of how dependency graphs are constructed in Mill and in the broader Mill plugin ecosystem. So that's the idea of object-oriented build. So while other build tools can have daemons, other build tools can track dependencies, I think this object-oriented way of modeling the build is actually very interesting and something very unique to Mill. I don't see anyone else who's done it before, using classes, methods, and overrides rather than using callbacks and global variables to model how to build a large multi-module JVM code base. So here's the last slide. I guess to sum up, there are kind of two angles to this talk. One is, I think Java build tools can be a lot better. A lot of ideas like keeping your JVM warm in memory, this is not rocket science. It can make your compile 15x faster, and Mill really demonstrates that there is a lot of speed up potential there. Things like automatically tracking dependencies, we've shown that it can work, and Gradle should do it, Maven should do it, rather than having you to manually decide which phase something to run in and possibly getting it wrong. On the other hand, I guess the other idea is that if you're interested in trying out something that's very different from Maven or Gradle, but is still able to work with many real-world JVM projects, you should give Mill a try. I can't promise you everything will work. It's still experimental. It's not as battle-tested as Maven or Gradle for sure. But what I can say is that it has a lot of very interesting ideas, including this object-oriented builds that I think translate into really good benefits, like the idea of being able to explore your build in your IDE, the idea of being able to reuse concepts you already learned to configure a build. These are things that the existing build tools have struggled with for many years now, and Mill, despite being a so-called newcomer, is able to provide to users. So I guess that's it. So the documentation site is mill-build.org. There's a GitHub. There's my email. You can try it out. All the examples here are downloadable and runnable. You can just download it and give it a spin if you're interested. And that's the end of the talk. So thank you for listening. Oh, questions are there. Why are other build tools so slow to build app? I don't know all the answers, but I know some of the answers. So Maven always runs cold, as we discussed earlier. So it also does a lot of runtime class loading rather than having one class loader, and each subclass loader does add overhead. If you load the class loaders and keep them around, not a problem. But if you keep recreating the class loaders every time you recreate the class loader, you have to rejig the bytecode and everything gets slow again. So for Gradle, I'm actually not sure the reason here, because Gradle does keep a daemon, it does keep the JVM warm. Somehow it's still slower, and I haven't really managed to figure out exactly why. How do you determine which tests need to run after changing the code? So we use the build graph. So this is for now it's pretty coarse-grained. We do this at a module by module level, but basically, if you change foo.sources, we run a breadth-first search through the task graph, and the breadth-first search will include, let's say, foo.test and crux.test. It will not include foo.bar.test because foo.bar.test does not depend on foo.sources. So it's a pretty naive, just do a breadth-first search and see who you collect. There's work to do to try and make it work within a single module, like doing the breadth-first search over the call graph or dependency graph rather than over the task graph, but that hasn't landed in the mill code base yet. Someone's working on it. Why did you choose Scala? This was originally a Scala project, only more recently gained support for Java, Kotlin, and other languages. But I guess part of the reason we need to use Scala, we want to stay with Scala rather than changing it is there's a lot of work that goes into making this work. So if I look at this slide, for example, I have a method calls another method, and I can capture that dependency at runtime to make a build graph. So I can use that build graph for my breadth-first, like topological sort and all that, right? But in Java, you can't ask a method who it calls in Java, right? You can't ask a method what file it's from, what line number it's from. You can't take a method and automatically convert its return value to JSON to put it on disk. So it does take some magic here. So the options are basically Scala, Java with a lot of compiler plugins and bytecode instrumentation, or Kotlin, again, with compiler plugins and maybe, again, some bytecode instrumentation. So all of these are possible. Like you could write a Java agent that does this for you and kind of mangles the bytecode to implement all these magic. But for now, the easiest way I found was just to use Scala, which the syntax is a bit foreign, but not needing to do all this like custom compiler plugins and bytecode rewriting is probably kind of wins out for me, and that's why it's in Scala. How do you specify dependencies in a more declarative way? I think it's basically the same as with Gradle. So Gradle does have some things that Mill doesn't. Like Gradle has a dependencies INI or properties file. Mill will probably get that at some point. Right now, there is a bot that is able to understand Mill's dependency syntax. I think it just parses it. It just parses the code out and looks for those strings in the code. So Depender bot doesn't work, but there's a separate like Mill Scala dependency bot that works for Java dependencies and other language dependencies as well. So we are trying to make this better, but for now, that's the state of the world. What about monorepos? Mill works quite well. I think the largest monorepo I've talked to is the largest monorepo owned by a person I talked to is about 1,000 submodules, and apparently he has no problems. If you look at Mill's own code base, I think Mill has about a few hundred submodules. Most of them in the test suite, just because it was cheap to make tests. It's cheap to make submodules in Mill, and it's not a problem. So if I go back to my Mill project, so this is the Mill build for the Mill project itself. I can ask, like, show me all the compilation tasks which will belong to all the modules. And yeah, you see a lot of them are in test suites because we made the test suite multi-module out of convenience. And if I ask Mill how many submodules the Mill build has, it's 463 submodules, mostly tests. But it has no problem, like it's not slow, you can run things from the command line very snappily, everything, even for pretty large modules. How to control caching custom tasks? There's a number of ways. The default is cache by default. Anything upstream changes, then I recompute from scratch. So earlier we saw this line count. All source files is upstream. If any of the source files change, my whole line count gets recomputed. There are options to make it more fine-grained. So you can make it recompute incrementally by keeping like the output folder or keeping the previous value and then kind of incrementally computing it. But if you want to do that, then it's on you if you screw up and then it becomes inconsistent. So there are ways to make it more fine-grained, but by default, we just wipe everything out each time upstream changes and recompute it. You don't need plugins, but can you use them? Yes. Extending Mill third-party plugins. There's a big list of plugins here by not me. These are other people's plugins that they wrote and put on GitHub. It's quite easy to publish a plugin. There's instructions on how to publish a plugin somewhere here. Writing Mill plugins, yeah. you can write your own plugin. And yeah, writing a plugin is exactly the same as how I showed you writing the build code, except you put in a class rather than an object, and other people inherit the class. So it's just take it and publish in Maven Central, other people use it. Extending mill does a lot of automatic configs, but you can override every custom behavior. I'm not sure what that means, so maybe I can skip this one, or I can ask again with a bit more detail. What happens when you calculate line count in resources and append a file? Will this recursive case be resolved? Yes, so calculate line count resources. I'm not sure why it's recursive, but basically if you change any file, we do a breadth-first search through the graph we saw earlier, and we'll recursively kind of recompute everything downstream of that change, modulo some of the caching optimizations you mentioned earlier.
Line in resources, and then add the file to the resources, then there is new file which has some lines. So
yeah.
It will trigger count line.
Yes.
Or not?
Yes.
So this is a recursive one. Or not?
I mean, it recursively looks within the resource folder. Is that what you're asking? Like you put something deep within a nested folder, it will get picked up. And if you put something like multiple steps on the task graph recursively, it will also get picked up. I'm not sure if that answers the questions. Are there commercial projects using Mill already? Yes. I mean, the ones that I'm aware of, the Chisel, like the new Sci5 chip development framework uses Mill. I know people at Disney Streaming and at Netflix who use Mill. I think those are the guys who have the biggest code bases that I'm aware of using Mill. So it's definitely not as big as Maven or Gradle. I can only count a small number of cases. So if you want to use something that's really battle tested, well established, you should not use Mill. But if you're willing to try something that's a bit less mature, but a lot of interesting ideas, then you can try using Mill on your own projects. What about SBT? SBT has a lot of problems I don't think I'll be able to explain these in a few minutes. It has some of the similar ideas, and Mill uses some of the similar ideas, like the idea of having a block of code that calls another method and having the dependency tracked automatically comes from SBT. But SBT has a very complicated build graph data structure that's 4-dimensional, very different from Mill's object-oriented objects, classes, methods model. And so it becomes quite hard to understand SBT, even though it has some quite good ideas in it. And the performance also has a lot to be desired. I think we're at time, so maybe we can call it a day. Thank you for listening, and hope you have a good conference.